So the purpose of this project is to find an alloy that performs well at 1000 degrees C and also prints really well. And in terms of alloy development for additive manufacturing, this is really the holy grail of what we want to achieve. So alloys that perform really well at high temperatures tend to be difficult to print, and the higher they can perform, the more difficult they are to print, they'll crack. And that means that for components that are designed for really high temperature applications in aerospace and automotive, the more complicated the component, the more difficult it is to print them. And so what we want to do in this project is come up with a material that has that really high temperature strength, but also prints really well. So you avoid cracks, you avoid defects, and this will really revolutionize the ability of additive manufacturers to produce components that are used in these high temperature, high performance aerospace components.
So the technology we've developed is a high gamma prime containing nickel superalloy. Key challenge is to make it both high temperature, strong at high temperature, but also processable by additives. So traditionally, the highest temperature nickel alloys have been processable by casting techniques, to some extent by forging techniques, but they've not been processable by additive manufacture, because the very characteristics of the alloy that make them strong at temperature also make them difficult to process. What we've done with our alloy design platform is to develop a series of models which predict the processability by additive manufacture of different compositions, and use those models in conjunction with the models we've got for strength and other mechanical characteristics to optimize for the purposes of additive manufacture. In so doing, we've created a whole new classes of alloys that are really the first nickel alloys in the world to have been designed bottom up for additive manufacture rather than modifications of alloys originally designed for other processes.
Currently, superalloys for additive manufacture are limited to around 600 degrees C. In this project, we wanted to design an alloy that would operate up to 1000 degrees C to improve the efficiency of combustion systems for aerospace applications. To do this, we used computational metallurgy and advanced characterization and testing techniques to rapidly develop the alloy. Normally it takes 10 years to isolate and develop new alloys. In this project, we've done it in 18 months.
The innovation that we've shown in this project has been to apply our proprietary Alloys by Design software approach. The material can operate at higher temperatures than other additively manufactured parts. Higher temperature operation in aerospace engines leads to higher efficiency. Higher fuel efficiency leads to a lower burn of fuel for the same goals. Additionally, additive manufacturing enables designs of components that are both functional and lightweighted, which means that the total weight of an aircraft can be reduced, which again leads towards fuel efficiency.
An important part of NATEP's overall role to us is as a cord, as a channel, if you like, that connects us to the UK engineering community. And the technology managers are really the makeup of that channel. They're the constituents of that channel. They provide advice as we structure the project. They monitor and provide feedback and ideas through the project. And they're the conduit to a lot of other opportunities to use the technology when it's mature.
Well, this project has been very successful, and it's great to see it come to fruition in the way it has. It's really a game-changing project which is really going to help the aerospace industry in the future. It's helping UK PLC stay at the forefront of technology such as this. And that's got to be good for the UK. It creates high value jobs, which is very important to the industry and really what NATEP is all about.